Um, so what we're going to be doing for the second exam is just start talking about integration. Um, there are 4 more classes, including this one before the exam. I do hope to finish the material by next Monday, the latest. I already made, just like 2 minutes ago, I made available the remaining MyLab assignments for the exam. Um, in case you want to check those out. Uh, But yeah, like in terms of like the second exam, like there will be like, if you have seen like the practice exams, which I will probably put the solutions tomorrow, just in case you want to compare it. But you should be able to do now like 4 out of the 6 problems, because those are like the non-integration problems. And then there will be like 2 integral problems along the lines that we will start discussing today. So it is more heavy on the non-integral stuff. Um, and the integral stuff that we'll do at the beginning for this midterm is more, I mean, simpler than what we'll do later on the final, where we have to do triple integrals, which is a bit more tricky. So let me just remind you like how integrals work in Calc 1. By the way, when I talk about integrals, I just mean like the definite integrals. So we won't discuss like indefinite integrals in this course for a long time. Like we'll use that a little bit towards the end. Um, we talk about conservative vector fields, but almost every integral that you'll see for the next few weeks will always have bounds. That's what I'm trying to say. So you will always need to evaluate them. You're not trying to find anti-derivatives, although they will appear in the process of like finding the integration, but all the integrals that we'll be doing for the time being will actually have some bounds. So let's just recall like the Calc 1 integrals. Right, so typically what you would have is something like this. And what this meant is that if you think of the graph of the function as some curve on the plane, I mean, maybe this is y equals f of x, and then the interval from a to b, let's put it here. Let's say the interval from a to b is this one. So the integral corresponds to, as you may remember, the area between the graph and the axis, with the just care that if the graph happens to go under, happens to be below the x-axis, then this area in the integral kind of counts as being negative, right? So it's more like a net area, because above the x-axis, the area is counted as positive, and below the x-axis, the area is counted as negative. So it's more like a net area, if you like, between the graph and the x-axis. So and a more useful way to think about it also is that, let me draw this again. Like if you want, the way in which you could think about finding this integral, right, in terms of a limit, is that what you would do is like, if you wanted to approximate the area, then what's better to do is kind of like break the interval into pieces, right? So like you break the interval a b into pieces. They could be of the same length, this subinterval, so that's not necessary. And then, on each subpiece, like you kind of like build a rectangle, whose height is like maybe the left endpoint of the graph or something like that. So if you have something like this. Uh, Right, so like this approximation of the area in terms of the area of the rectangles is not perfect, but the idea is that as you shrink, the width of the interval, sub-intervals, this is supposed to behave as a better approximation. So secretly, it's not something like you would use much in practice, but if you wanted to define the integral as a limit, like it is kind of like the limit of all these areas, right? As the width of the rectangles approaches zero. The important thing of that for now is just that if you think about it as in terms of these smaller pieces, then you're really kind of like adding, you're adding area. So the integral is really just like a way of doing like a sum. So it's just like the terms that you're adding are really, really small, right? So it's kind of like an integral in the end is like a sum of the terms. If you think about it, if you think of if you call the width like delta x, so then like the area of this rectangle is like base times height, so it's kind of like delta x times the height. Okay, so in reality, like, the integral becomes useful when the quantity that you're trying to compute is some sort of like, can be broken into pieces that can be added, right? So integration is more of like a strategy for like, finding like a thing in terms of like smaller parts that how to compute like more easily. Okay, and then there's like basically the same story happens for us when the function happens to depend on two variables. So what we want to start talking about today is what we'll call double integrals. So a single integral in Calc 1 was for a function of one variable, right? The integral that we're going to start discussing for today, it depends on two variables. So instead of calling it y equals f of x, you'll call it like z equals f of x comma y. Okay. And so the idea is so the idea is going to be that now you look at the graph of the function, and remember the graph of a function of two variables is some sort of surface. So you have some sort of surface in space. Yeah, okay, this is a little bit harder to trickier to draw. So I'll just draw something like simple like that. And below on this side, like you would choose like an interval on the line, right? On the x-axis. Here, like you could, like for example, here are some things you could choose. You could choose like a rectangle, right? You could also choose like a triangle. You could choose like a this, so you could, or like an ellipse maybe. So you could choose something like this, this, or you can choose like more random stuff. So you could choose like a piece of the plane, which I'll just like try to draw in a way that looks a little bit more like amorphous. So any of these corresponds like to a region of the plane, right? So R is going to be here like a region of the plane of XY plane. And the idea is that there is, if you think of the graph as some sort of surface that sits above the plane, well, it could also be below the plane, depending on how the graph looks, right? But if you think about it in that way, then there is some sort of like, volume between the graph and the plane, right? Which is the one I'm trying to show you here. And so that volume is what we would like the double integral to find. And volume is also in quotes in the sense that it would be kind of like a net volume, in the sense that if the graph happens to go under the plane, then you want to count that as negative. So what I'm trying to go up, like what I'm trying to say is that we want to find things like can look like this. Okay, I'll put it like this. Okay, so this will be our double integral of that. Let me see if I can move this just to make it easier. Over region R. And again, that's supposed to be some sort of net volume. Between the graph and the XY plane. That makes sense. Are there any questions about this so far? So good. I was going to show you first some like animations that are kind of useful for this stuff. Um, make it more clear what's going to happen. So. Okay, so let me, yeah, I think this is a good moment to show the animations. So the idea here is to take a similar strategy to what we did with the derivatives. So if you remember, the way we were working with derivatives is that we talked about this part of derivatives. So at the end of the day, like to find the derivatives, we only computed like regular derivatives from Calc 1, just with the extra care that you have to pretend like one of the variables was constant while you're computing the partial derivatives. Here we're going to do something similar. So when I write something like this, right, there's going like as you can see from writing it, there are like two symbols for integration, right? So what that means is that we will end up doing two integrals, okay? But the way that these integrals will work will be similar to like the situation with the partial derivatives in the sense that we will integrate one variable at a time, if that makes sense. So let me show you what I mean by that first by doing some like just like showing you some like animations. So so here's like one animation. So let's say your function is just like x squared plus y squared plus 1. So that is like the regular paraboloid just shifted by 1 unit. So the graph of the paraboloid is what you see here in gray, okay? And then you're just looking, for example, at the stuff of the paraboloid. Let me see if I can make this a little bit bigger, actually. Um, no, let's say you're just looking at the stuff of the paraboloid, like the part of the graph that's above this rectangle. So there's like a rectangle you can draw on the plane. In this case, like the rectangle is like x goes from -2 to 1 and y goes from -1 to 1. Okay, so that's like the rectangle. I think it's easier if I just show it to you from this perspective. So there is some region of the graph that's above this rectangle. Okay. Which is this piece, and then the volume between this surface and the rectangle is what the double integral is supposed to compute for you. Okay. Um, Now in practice, there is a similar story that happens here, where like if you how would you try to find this volume, right? You can take a similar approach to what you did with integrals in Calc 1. So, which is what I had drawn here. So in Calc 1, like what you would do is kind of break the interval into pieces and then like find the area of rectangles, right? In this case, what you could try to do is, break that rectangle into pieces, like into mini rectangles, and find the volume of those like, boxes or um, that lie above each rectangle. So let me see if I can show you that here. Yeah, so let me see if I can. So that, I don't know if you can, yeah, hopefully you can see like these boxes, right? So you're like, you break the rectangle into pieces. Like for example, like this is like a very crude approximation. You don't break any, like the rectangle at all. So you just are working with the volume of one box, but then you break it into 4 boxes, and then like 3, and so on. So you can continue breaking it into more and more pieces, and the more and more, the smaller the subdivisions. Let me see if I can show the solid again. The smaller the subdivisions, like, the better this will be as an approximation of the volume. So, okay, the animation is kind of slowly dying. Let me see if I can zoom out here. But so the idea is like that there is like an approach in terms of sums, which were called Riemann sums, by the way. There is an approximation you can do in terms of sums for to compute these double integrals. And so, secretly, the way in which you can find these double integrals is in terms of like a limit. Okay, so let me see if I can show you another animation here. Okay, yeah, this one is probably a bit better. So you have, again, you're looking at kind of like the volume is above this square, and then you want to approximate it with these prisms, and then as you take more and more approximations, like the idea is that as you take smaller and smaller divisions, sorry, that's what I meant. The idea is like the difference between the total volume that you're after and the volume of this, like the sum of the volumes of these prisms, like decreases more and more. So in the limit, this should yield the volume that you're after. Okay, so what I'm trying to say is that I still need the animation, but what I'm trying to say is that if you break, if you break like the region into pieces, so if you break the region into pieces, like let's say each piece like it has some area delta A, uh, then this is some sort of like sum of the terms of x, y. Okay, so the point here is that this is also like some sort of limit, just in the same way in which this is also like a limit as delta A goes to 0 here. Okay, does it make sense up to now? Any questions about it, about this? Okay, so that is conceptually what this is supposed to find for you. Um, again, it has like many applications just because if you think about this as some sort of sum, then you can use this stuff to find like different things like the total mass of an object. For example, how would you find like the total mass of a solid? Like you break the solid into mini pieces and then you add up all those like smaller masses, which are supposedly easier to find. So like that ends up being like the same as an integration. Also things like for moments of inertia and other things, average values, many of like the things like that you could try to compute, like as long as they can be broken into pieces that you can add in some way, they can be represented as integrals. So there are many things like do fall into like the idea of like integration. Thankfully, the idea is like we are not really going to learn like new ways to find integrals. A lot of the stuff that you already did in Calc 1 can be reapplied in this context. You just have to be a bit more careful. So the idea is, the way, again, like we're trying to find the volume of this region. So the way I just explained this is that you can kind of break the region into mini squares, for example. That's one way to think about finding the volume. But there are other ways you can break the region to compute the volume, which end up being more useful just because it's more closely related to what you would have done in, say, in Calc 1. So let me try to explain what I mean by that. So okay, so for example, let's say, if I can show you this here. Okay. Okay, so let's say that, again, the graph now looks like this, and you want to find the volume between the graph and the region is above this rectangle, right? So you're trying to find the double integral over this rectangle, okay? One approach to finding the volume is like breaking it into mini rectangles, which is what's being shown in here. Another approach, which is, if you want to think about this more concretely, like, you could think about, okay, maybe this represents like the shape of a very weird type of bread. Okay, so it is like a solid, right? Like if you think of the bread with like as a solid that you're going to split among friends, right? So usually people don't cut bread like in boxes, right? Like you never see people cutting bread usually like, in rectangles, like almost no one does that. What you do is like you take like a knife and you slice it this way, right? So that is exactly what's being shown here, right? Like if like imagine that you take a knife and you start like cutting the bread this way, right? So you get all like these slices. So just imagine that this slice has a little bit of thickness, right? This yellow slice here. So one way to think about the total bread that you started with, right, is just like, maybe if you make 10 cuts, right, with your knife, like, the total amount of bread should be what you like exactly the same as all those 10 slices of bread that you get after doing like the cups. So what I'm trying to say is that if you start imagining like cutting the region, using like with a knife, using like this, well, let's take maybe call these vertical slices. I'll show you that more precisely what it means. If you cut the bread using those slices, then yeah, you should still have, it is still the same bread, right? Like if you were to somehow glue the slices together, you would recover the same 3D object, right? And then like likewise, another, so I mean, like next time I'll have to bring a piece of bread. But another way, like, so I'm kind of doing like the slices this way in the animation, but another way, like you could cut the slices, which is traditional in the bread is like cutting it this way, right? So you could kind of like just like use like slices that go, the cuts that go like in a orthogonal direction. So if you cut it that way, which is what you see there, right? I mean, it's kind of still the same principle, right? If you make like, I don't know, maybe you made 10 cuts there, so you get our 20 cuts now. So you make 20 cuts here, you get 20 pieces of bread, right? 20 slices, and but again, if you put all the slices together, you would still get the same bread you started with, right? Assuming that there are no crumbles, everything, the cuts were perfect, or like the mass is conserved or whatever, right? So what I'm trying to say is that, when you have a solid, my point is that when you have a solid, there are many ways to chop it up into pieces, right? So one way is kind of like using these boxes, like that showed you at the beginning, but other way is kind of like, you know, to use like this, like more like horizontal or vertical slices to cut it up, which is more closely related to, how we would actually cut pieces of food like bread, right? And then next time when we talk about polar coordinates, I think we'll do that next time. There are other ways which are more natural depending on the region to cut it, like for example, a pizza, right? Because a pizza, like you buy a pizza, you wouldn't cut in neither of these ways. Like usually you use something, which is like starts at the center and like then more like a circular cuts or radial cuts. So the point is that all of these like ways to cut, if you have like the region, like in space, like this volume, it doesn't matter how you cut it, it still has to represent the same volume, right? So all these different methods of like computing the volume should yield the same answers. The difference that like the advantage that a method like this has, is that when you cut it this way, what you'll see happen is, I'll show you this in a moment. When you cut it this way, what happens is that one of the two variables, X or Y, remains fixed. Okay, so the advantage of doing cuts in this way is that you're kind of just like changing one variable at a time. So that makes that this process look very similar to like, kind of like a partial integration because like only one of the two variables is being varied. Does that make sense? Okay, so let me show you like, and that's exactly like basically how we'll start computing all those integrals. So let me do some diagrams and that's basically how we'll always do this. Let me see. So the idea is just to cut the region. Yes. To cut the region. In such a way that only one variable changes, only one of the two variables. So what do I mean by this? Let's start with like cuts that will be vertical. So here's like one possibility. Option one. Okay, so like imagine, and for today, we're okay. So the thing with these problems is that philosophically, it's always all of this form, but like what makes this a bit more interesting is like the shapes that you can make, like the shapes on the XY plane that you could use. So you could have like rectangles, you could have triangles, discs, more complicated things. So we kind of have to go build up slowly, the different ways to do this process. So I'll start with the easiest possible region on the plane, which would be like a rectangle. So that is like, that is the easiest way thing you could think of. So let's say that you have like a rectangle, and it doesn't have to be, the rectangle could be anywhere on the plane. So I'll just um, put it in here. Okay. The region, my region R is just a rectangle. So again, like the graph, I'm not showing you the graph here, but you have to think that the graph is somehow above the rectangle, right? And so we're finding the volume between the rectangle and the graph, okay? So if I make vertical cuts, right? If I make vertical cuts, what I mean is that if you think of the slices, I'm going to kind of slice the rectangle this way. Okay, so the idea is that along a particular cut, right? So it's kind of like in those magic tricks also. So when you make a cut, right, along a given cut, fixed cut, um, or like a given vertical segment, right? So for any of these vertical segments, so if you look at any of these segments, what's happening here is that the two variables x or y, the variable that's changing is y, right? If you just focus your attention on one of these vertical segments, the variable that's varying with like the one that I'm varying with my finger is like the y variable, right? X is being held constant. So for any of these segments, y is changing, right? Y is changing and x is fixed. Is that making sense? Like, uh, so the idea is like, you make all these cuts, or like one way to think about it is like you make a cut, and then as you vary where you place a knife, that's how you recover the entire piece of bread. But like the important thing is like when you make one of these cuts, you're only varying the y variable. So the way that's reflected when we do the integral is that when we integrate this, we are going to integrate first with respect to y because that's the variable that we're changing. Okay, so when we have something like this, if we do these vertical cuts or vertical cross sections, let me put it like this. So we have a function that depends on x and y, but we're going along each of these slices, only y changes. So what that means is that we're going to integrate the y variable first. Okay. And whatever we get, we will integrate later with respect to x. So I'll put it like this. Okay. So what this means is that we'll integrate first. So here, this means like integrate first with respect to y. pretending that x is a constant. Okay, and then after you do that integral with respect to y, like when you do an integration with respect to one of these slices, as you start moving the slice or the cut, that's how you recover the entire piece of bread. But to kind of move where I place my knife, then I do have to change the x value. So you see where to decide where to start moving like where I place a knife, I'm varying the x, so that's why the integral that remains will be with respect to x, and let's put this here between x min and x max. Okay, so that will be the first integral that we'll do. But I think I'll do like an example before showing you the other method. Um, but the idea is that the idea is that it will be really like an ordinary Cup1 integral with the extra care that you have to pretend that one of the variables is constant. So it's kind of like some sort of partial integration, similar to like how partial derivatives work. Is that making sense? Let me do an example before continuing. So let's say that the function is just 3x squared y to do something simple. And the rectangle, I'll choose like a simple rectangle, like I'll put it in here. So this is my rectangle. Here 0, 1, and this is 1, 3. So again, like you have to imagine there's this graph of the function, and we're looking at the volume between the graph and this piece of the rectangle. What I'm saying now is that we're breaking the rectangle vertically, okay? So along one of these vertical slices, like y is changing first. So if you wanted to, so what this is saying is that if you wanted to integrate the function 3x squared y in this way, what the method says is that you integrate first with respect to y. So put here 3x squared y. So I'm going to integrate first with respect to y. And whatever I get, I'll integrate then with respect to x. So it is do an integral and then integrate the answer of that integration. Okay. So it's like an integral of an integral in a sense. So between and as I mentioned at the beginning of the class, all these integrals for us are kind of definite, so they always have bounds. So you have to put the y values and the x values. So the y values are like the smallest and largest value that y takes in this region. Again, because we're working first with rectangles. I'll show you in a bit how you have to adjust things a little bit when it's a more complicated situation. But in this case, the y values go from 1 to 3, right? So you want to say that the bounds go from y equals 1 to y equals 3. And the x bounds go from 0 to 1. So x equals 0 and x equals 1. So that's how we are going to do the first integral. Okay, is there any questions about the setup? In all these problems, like finding the bounds, will be the hardest part of the problem, you'll see. Uh, again, like this is like the most simple region you could think of. So like, but like while start doing it's increasing like the level of difficulty in the in the region. But really, like most of the interesting stuff when it comes for us to these double integral problems is like just finding what bounds to put. Which again, for now, is like relatively easy, but you'll see as the problem becomes more complicated, it's like more interesting thing to figure out. Uh, so usually like the majority of the problems, points on this problem just go to setting up the integrals because the way to do the actual integrals once you have the bounds is no different from how you do like calc one integrals. So in this problem, what this means is that you're integrating first with respect to y. So again, think about it similar to like a partial integral. I mean, it works like similar to a partial derivative. So we're kind of doing like a partial integral of sorts. So if you're integrating first with respect to y, then 3x squared is like a constant, right? So like the integral of y dy is just y squared over 2, right? So that's is basically what we're integrating. So So I'm going slowly because again, like this is kind of like the first time we're doing this. But what I'm trying to say is like the integration is just you know, 3x squared y squared over 2. Okay, and being a definite integral, you are supposed to plug evaluate at y equals 1, y equals 3. And what this is like what the method says is that whatever we get, we integrate with respect to that. So kind of showing you all the steps. So like the next step will be just to evaluate this at the proper bounds, right? Is that okay? Is that making sense? So let's see. So um, so what happens when you put y equals 3 here at the beginning? So you get 3 squared, which becomes 9, right? 9 times 3 is 27. So you get 27 x squared over 2. Right, that's what you get at y equals 3, and at y equals 1, you get 1 squared. Okay, so that's just 1, 3 times 1, 3. So you get minus 3x squared over 2. And then whatever this is, you integrate with respect to that. Okay, so this will just give you 24x squared over 2, so 12x squared. Okay, and this is an easy integral, just what, like 4x cubed. By the way, should have said this. When you find all these integrals, you tend to put like a plus c, but they kind of like go away because we're really just like doing like the definite integral. So if you remember, they're like adding the constant of integration like doesn't make a big difference because like when you evaluate, like it always disappears. So that's why just like putting it like this. So you just get that. Okay, so the double, what this is saying is that the volume would be for in whatever units, like the volume that you are using. Cubic feet, cubic meters, whatever. But the important thing here is that, again, when you're doing this integral, you're really just like integrating one variable at a time. That's kind of like the takeaway of like the most important thing that happened for this type of problems. Is that okay? Okay, now my point is that you can do this in a way that reverses the cuts. So instead of like cutting vertically, right, you can also cut it horizontally. Okay, so at least let me see if I can write. Okay, so The second option is to do horizontal cuts. And it's exactly the same idea. Okay. Uh, but now I'm going to cut the region horizontally, so I'm doing cuts that look like this. And then now everything kind of gets reversed. So for any of these segments, the X is changing. And now Y is fixed. So again, if you just focus your attention on any of the horizontal segments, you see my finger is only moving in the X values for a particular segment. Okay. So what that means in terms of like the integration is that we integrate now first with respect to X. That's basically what that means. So when you have the double integral, now the idea is to kind of reverse like or that's what you would call reverse the order of integration. You'll do things, but in the opposite order. So you would integrate first with respect to X. And whatever you get, you will integrate with respect to Y. So here, the bounds for X are from the minimum value of X, the maximum value of X, and from the minimum value for Y, the maximum value for Y. Okay, but now again, this means integrate first with respect to X, pretending that Y is a constant. Okay, great. First, with respect to X. Okay. So let's just do that this thing exactly for this problem with this function and rectangle as before. So let's do it for the same rectangle. So here you have 1, 3, 0, 1. And now the cuts look horizontal. So again, now I'm going to integrate first with respect to X. And then the rest with respect to Y. So this is now, okay. Again, the bounds go for the minimum value of X. Now the minimum value, the minimum value of X is still 0. So X equals 0 to X equals 1. And then Y equals 1 to Y equals 3. Okay, so really it just looks like, at least in, for the rectangle, you'll see, you have to be more careful in general, but at least for the case of the rectangle, you're really just flipping like the order in which you are reversing the order in which the like the integrals appear. Okay. That okay? Questions about this bounce? Okay, and so if you integrate first with respect to x, now that means consider x as the variable and y is just now like a constant. So 3y is like a constant. So you're really integrating x squared, right? And you know the integral of x squared is x cubed over 3. Right, so the three by the since it's x cubed over 3, that 3 gets canceled with this one. So you are really just getting like um x cubed y. That's like the antiderivative if you like. Um, and this is how we evaluated at x equals 0 and x equals 1. Whatever we get, we integrate with. Right, because the derivative is like an antiderivative, but it's kind of like the derivative with respect to x gives you what's inside, right? So it's like it's like the partial derivative of this with respect to x gives you 3x squared y, in the same way in which the partial derivative with respect to y gives you the other thing. So it's kind of like, again, like an antiderivative, but like either in x or y, depending on which integration you're doing first. And then, I mean, this one is easy. So when x equals 1, you just get y. And when x equals 0, you just get 0 here. Okay, so it's you're just integrating y dy, um, right, which is just y squared over 2. Okay. So that's 9 minus what? 9 minus 1 over 2. So that's 8 over 2, that's 4. Right. So you'll notice that it is the same number as before because like you're literally computing the same thing. You're just computing the same thing in different ways. You're like, again, if you think about it in terms of the bread analogy, you're just saying like to split the bread among people, like you can cut it like vertically or horizontally, but it's still like the same bread. So it cannot, like the total amount of bread you started with cannot change based on how you cut it, how you slice it up. Um, Is that making sense? Okay, let's do another one, which have now a bit more interesting. And then next time I'll give you kind of more like the general rules of how this work, and then we'll start talking about polar coordinates, which is another way to do this. And that's like the polar coordinates will be the last topic for the exam. Let's first like do another example to. Okay, so let's take the function to be. To be, just to put something simple, x times y. Um, and again, we'll do more interesting examples later on. The function itself is not too important. That's just something to actually have like the integral to do perform at the beginning to compare the numbers that we're getting. Again, typically, the thing that's more interesting here is the how do you set up the bounds so that. So what's more important is that the region, like what's interesting is what happens with the bounds for the region. So now the R is going to be the inside of the triangle with vertices 0, 0, 1, 0, and 1, comma 2. Okay, so let's just draw any this type of problems you have to be relatively used to drawing the region. Like the regions like typically will be their lines, circles, parabolas, like nothing too crazy if you're being asked to draw it. But at least you have to be comfortable like drawing the regions if it's something like of that sort. Like so triangles, rectangles, discs, like that's kind of like the typical thing that you will need how to draw. So so the vertices are 0, 0, 1, 0, and 1, 2. And the region itself is this triangle. Okay, so our region is a triangle. And then now the interesting thing is that by not being a rectangle, there are some small changes that you have to make when you set it up um, in the integration. So this always happens. I don't think I need this. I'm gonna go ahead and turn this on. Hopefully it will start. Hey there. Big mistake to have restarted it. So let me draw this. Okay. No, we'll try not just. That's fine. And then, yeah, I don't know why these always like to turn itself on after a certain number of minutes. But So in the first approach, we were using like you break the region making horizontal vertical cuts, right? So when you break it this way, again along each of the lines, each of the segments, the variable y is changing. So what that means is that the integral becomes an integral first with respect to y. And then whatever you get, you do with respect to x. Okay. Now, here's the interesting part in this problem because this is an integral first with respect to y, so you have to put the y bounds. Okay. So the y bound represents which values y is taking along one of these like vertical segments. Now the thing is like if you look if you look at the vertical segments, one thing that you notice here compared to the rectangle case is that in the case of the rectangle, all the segments had the same size. That's kind of like the crucial difference, right? When you drew this for the rectangle, every segment was of the same size, right? But here now, like the segments are literally increasing in length as you move along, right? So somehow the bounds need to reflect the fact that the segments are getting bigger and bigger as you change the value for x. Is that making sense? So that what I'm trying to say is that the bounds cannot just be like fixed constants, at least not both of them, because if you put like 3 and 5, for example, then you would be saying like the values for y in every segment is always the same. And that cannot be the case because like, as you can see, like the length is changing. So one way to think about it, which is a little bit more like dynamical, is like if you put some arrows to these segments, kind of like in almost like a video game where like you have like all these arrows moving through the region, like the region being like the triangle. So if you think about all the arrows, like these vertical arrows, they are all going through, they're going through through the x-axis, right? And the equation of the x-axis is just y equals 0. Okay, so that's why the lower bound is going to be y equals 0. But then the arrows, if you just follow any of these arrows, whichever arrow you take, they exit the region, right, through the equation of the hypotenuse, right? And the equation of the hypotenuse, well, I mean, you have to find it, but you have the vertices, so it's easy to find. The equation of the hypotenuse is just what, y equals 2x. So that's great because it's giving you y as a function of x, which means that the y value depends on x. So it's a way of saying that, how big y is depends on where you stand, which makes sense. So the bounds for y in this problem are from 0 to 2x. Okay. So that's saying that and that's kind of reflecting the fact that you know the length for these segments are not all of the same size. Does that make sense? Kind of reasonable questions about this. So the bounds like cannot be like constant numbers in both cases because again like they are not like the size of these arrows are not the same. And then the bounds for x, and I'll write all these rules more precisely next time. I'll just finish the example today and be done with it. But the bounds for x is just like between which values of x do you need to move these arrows, right? So the arrows need to be moved from 0 to 1 to kind of recover to sweep out the entire triangle. So the bounds for x is still are between 0 and 1. And what else? Again, I'll write this like next time as like a set of rules, but the rule is kind of like the outer bounds or the last bounds of the integration are always like constant numbers, basically, because somehow like the inner bounds already account for the variation in the size of the arrows, basically. And once you do that, then the problem is really indistinguishable from what we were doing before, meaning that you're going to integrate first with respect to y, pretending x is constant. So the integral of y is just y squared over 2. You get x y squared over 2. That's going to be evaluated at y equals 0 and y equals 2x. And then whatever you get, you will integrate from 0 to 1. So when you put y equals 2x, you get 4x squared. 4x squared, you get 2x. You get 2x cubed here then. And then y equals 0, there's nothing to put, right? So that's what you end up integrating. And so that's just what? X equal 4 over 2, right? And then that's 0. So the answer is 1/2 in this case. Is that okay? Making sense? So far, so good. Questions about this? Okay, let's switch it up to see like if you know how to fill the gap here, like for the bounce, and you really understand what's going on. So let's see how this would look if you do the same process, like the same problem, but switching like the cuts. So now I'm going to do horizontal cuts. Okay, and then and again, well, we did say that what the equation was y equals 2x, so I'll put here y equals 2x, and this is 0, 0, 1, 0, 1, 2. Okay, and so I want to do the integral. But obviously, in practice, like you only have to choose one of the orders because they always give the same answer. I'm just doing it in both ways so that you can see how the bounds look from one order versus the other one. But in practice, of course, you can choose like whichever you prefer because that's the point. Like you'll see like we'll do next time examples where like one ends up being easier than the other. I mean, there are like sometimes preferences for using one over the other, but it's more specific to the region. But theoretically, they're kind of always theoretically they will always give you the same answer, but it's just that sometimes for practical purposes, one can become easier, and the other can become either extremely hard or almost impossible. So you'll see that next time when I give you some more examples. But for now, let me just finish by doing it this way. So now the idea is to integrate this with respect to x first. And so what that means is that you have to put the bounds for x first. And again, it's kind of like a similar process here, in the sense that the bounds for x cannot they cannot just be of the same size because you can see like these segments being taking different values. Okay, so one way to think about finding the bounds here is analogous to the previous case where you can draw some arrows. So instead of drawing them as segments, draw them as arrows. Now the arrows are moving horizontally. They move from left to right because the idea is that they have to move in the order where the variable is increasing. So x increases from left to right in the same way in which y increases from south to north, for example. So if you move the arrows that way, one thing you can notice, like maybe it's actually easiest to notice this one. All the arrows, right, like the place where all the arrows stop or exit the region, all the arrows exit the region through this side of the triangle. And that side of the triangle is x equals 1, right? This is like where x equals 1. So the top bound which will be the x place, will be x equals 1. But now, all the arrows enter the region, right? Just imagine shooting a bunch of arrows to the triangle. So all the arrows, like all these incoming arrows, enter the region first now through the hypotenuse, right? The equation of the hypotenuse is y equals 2x, but here's where you have to be careful because this is supposed to be bounds for x, right? You're trying to find an equation for x. So the equation for x is the same is the equation of the parabola, but in terms of x. So you have to solve this equation for x to say that x equals y over 2. Does that make sense? So it is the same equation, it's just like psychologically the roles have been reversed, and it makes sense because the point of changing the order of integration is that you're reversing like the roles. Like so now x goes first in the integration and then y. Okay. And the last step is that you have to put the y bound. And for the y bounds, it's again like what is the you have to say here like what are the values that you have to move these arrows to recover the entire region. So you have to, like the first arrow you have to draw is at the bottom, y equals 0. And then you have to increase the height of the arrows until you get to this vertex, but this vertex is at y equals 2. So the bounds for y now go from y from 0 to 2. So when already for the triangle, when you reverse the order of integration, the bounds are not just like, it's not, it is different from like just flipping the order. You cannot put these bounds here, like you do have to adjust it according to the picture. So once already you're no longer dealing with a rectangle, you cannot just like, kind of naively translate the bounds from one place to the other. You do have to think a little bit better in terms of like the picture of what's going on. And that's why, all these problems, the interesting part to a large extent is to just figure out how to set it up. Because once you have the correct bounds, really like the integrals are just like regular Calc 1 integrals. So for example, how do you integrate this? Now you're integrating with respect to x first. So gives you x squared over 2y, that x equals 1, and x equals y over 2. And whatever you get, you integrate from 0 to 2 for y. Okay, so I'm almost done. And so yeah, when you do this, you get x equals 1 gives you y over 2. And then x equals y over 2 gives you y squared, y cubed. So it gives you y cubed over 8. So that's what you want to integrate in the end. And this is just what? Y squared over 4 minus y to the 4 over 32. So that gives you 1/2. So again, like the integral gives you 1/2, which is what you have found before, because they are supposed to coincide. I mean, they always need to give you the same answer because they are finding the same quantity. It's just, this is just saying that there are like good natural ways to find the quantity, and like that's what I'm showing you right now. So what I'll do next time at the beginning of the class is kind of give you more like the general rules of how this works out. Do some more examples slightly more complicated, and then we'll start talking about polar coordinates, which is the last topic for the midterm, which is how to chop off, like polar coordinates is just how to break the region more like suited for pizzas, like, so you make like radial cuts. Here, like the cuts are horizontal or vertical. In polar, like the cuts are radial, like kind of like how you would cut like a pizza pie. Okay, so we'll start talking about that on Wednesday. That sounds good. So let's end here.